Here's problem 3119. A conducting bar of length L rotates with a constant angular speed of +2 radians per second about a pivot P at one end. A uniform magnetic field magnitude 0.2 Tesla is directed into the paper. If L is 0.4 meters, what is the potential difference VA minus VB? Let's look at this situation for this blade moving about this pivot P. And we're told we have a positive angular velocity, which means that we're actually coming out of the page because the angular velocity vector would be out of the page. By the right-hand rule, that means we are going counterclockwise, and we have a magnetic field that's into the page. The value of that is 0.2 Tesla. If we were to consider an electron on this conductor, and it's moving as this is rotating counterclockwise, it would have a linear velocity that is going like this. And if we do the cross product between V and B on this, we would be pointing to the left, but then for a negative charge, there will be a magnetic force on all the negative charges that will actually be to the right. What this means is that we're going to end up with a lot of negative charge developing on the B side of this conductor, and for that matter a lot of positive charge developing on the P side of this conductor. So point A is at a lesser voltage than point P, and B is at a lesser voltage than point A. So we'll have to think that the potential, if we consider point P as our reference potential of 0, A is going to be negative, and so is B, and A is going to be more positive than point B. So we'll keep that in mind. Okay, as we calculate this, what we're going to do is find the potential at A and the potential at B separately with respect to our reference at point P. The length at point A is going to be half the length of the whole rod, which is going to be 0.2 meters. The length at point B is going to be 0.4 meters. Our angular velocity is conveniently given as 2 radians per second. And we are going to employ in general that the magnitude of the voltage is going to be equal to the magnetic field omega length squared divided by 2. So the magnitude of the EMF to point A is going to be equal to the magnetic field omega length to A squared divided by 2, which is going to be 0.2 Tesla times the angular velocity of 2. Length to A is 0.2, that squared, over 2. 2's cancel out. We have 0.2 times 0.2 times 0.2, which is going to be 8 times 10 to the minus 3 volts. Okay, or 8 millivolts. The potential at point B, the magnitude of it, is going to be B omega length to B squared divided by 2. So that's going to be 0.2 Tesla times 2 radians per second. 0.4 is our length, that's squared, divided by 2. And this is going to be 32 times 10 to the minus 4, or 10 to the minus 3 volts. Well, the potential at A is negative. It's in relation to at P. So the potential at A is going to equal a negative 8 millivolts. And the potential at B is negative with respect to point P. That's going to equal a negative 32 millivolts. So the potential at A minus the potential at B is going to equal a negative 8 minus a negative 32, all that millivolts times 10 to the minus 3. 8 minus a negative 32 is going to be 8 plus 32, which is 24. So this is going to be 24, positive 24 times 10 to the minus 3 volts, or positive 24 millivolts. So that has the potential difference, VA minus VB on this rod, a positive 24 millivolts.